With this screencast, I want to try to complete some of the ideas that I developed in class today. Today's date, February 25th, 2014. So again, I want to work with one equation that we're comfortable with, this second order differential equation that comes from the model of a damped harmonic oscillator, has this corresponding linear system and two solutions, one e to the minus 2t. The derivative of e to the minus 2t is the velocity, so that's this term. E to the minus 2t describes position. The second term describes the velocity. And the second solution was e to the minus t, with its derivative describing its velocity as negative e to the minus t. One of the things I want you to notice is that if I factor out an e to the minus 2t here, I'm left with a simple vector 1 minus 2, and in this case I'm left with the vector 1 minus 1. These solutions are in fact straight line solutions because they're just constant multiples of a particular direction. So here's the direction 1 minus, here's 1 and minus 2. And that places us here. I go over 1 and down 2. It places us right here. And as you read this, you should feel comfortable seeing that this is just a constant multiplier. As time goes on, this term starts at t equal to 0 at the value of 1, and then goes to 0 as t goes to infinity. And so our solution starts here and moves along this line, heading towards the equilibrium point 0, 0, but never reaching it, because as t goes to infinity, there's no time where this term will actually be 0, but it'll get infinitesimally close to 0, and clearly we're approaching 0. Similarly, in this solution, we're on the line 1 minus 1, go over 1, down 1. We start right here at t equal to 0, and we move again towards 0, 0. In the next section, 3.2, we're going to talk about how we generate these straight line solutions and under which circumstances do we find them. But whether they're straight line solutions or not, they are two solutions. And in the linearity principle and in the theorem that came at the end of the section, we see that using two linearly independent solutions, we can generate any other solution. So if I give you an initial condition here, let's say at 1, 1, suppose at time 0 I'm here, and I'm looking to somehow generate the solution curve that would go through that point, and it looks as if it would do something like this. It will be through a linear combination, a sum of these two known solutions, that will allow us to find the solution through any point on this plane. In question number 26, so I want this first example to be similar to what is asked of you in your homework in question 26. And so I'm going to go to the next page and talk about that using the same example. In part A of question number 26, again, this is a similar example, so I'll say similar to homework number 26, section 3.1. They say to demonstrate that something is a solution. So you're asked to say show that y1 of t equal to e to the minus 2t negative 2 e to the minus 2t. Show that this is in fact a solution of this system, which I'm denoting by star. System, the matrix A times Y. And so I begin by taking two steps, the derivative of y1 with respect to t, which gives me a minus 2e to the minus 2t and a 4e to the minus 2t. And I think I did this in class, but it doesn't hurt to do it a second time. That's the derivative. What happens if you, so it'll be a solution if a times y1 also equals minus 2 e to the minus 2t and 4 e to the minus 2t. So the matrix A for this system is 0, 1, minus 2, minus 3. The vector y1, the solution vector, is made up of e to the minus 2t and a negative 2e to the minus 2t. And when I do the matrix multiplication, I get, so I take this row times this column, the 0 multiplies this term, and the 1 multiplies this term, and I end up with just a negative 2e to the minus 2t. And then on the second row, the minus 2 multiplies this term, the minus 3 multiplies this term, and I get a minus 2 e to the minus 2t. A minus 3 times a minus 2 is a positive 6 e to the minus 2t. And sure enough, that is minus 2 e to the minus 2t and a positive 4 e to the minus 2t. And so the result of differentiating the vector gives me this. The result of multiplying a times the solution vector gives me this. And these two things agree. This vector agrees with this one. And so yes, it's a solution. Okay. That's the first part. Finally, as I'm working an example similar to number 26, in section 3.1, the second part of the question says, find a solution of the initial value problem where here's our linear system that's described this way, and here's the initial condition, y of 0 is minus 2, 4. In general, we're going to need two vectors to answer such questions, but in this case, given that our known solution, y1 of t, which we wrote in a more concise way is e to the minus 2t times the vector 1 minus 2. This vector, this solution function, it's a vector, yes, at time 0, is at 1 minus 2. And I tried to show, it's very hard with this application to draw straight lines, but here is the straight line solution that lies along the line 1 minus 2, and I tried to extend that line forward and place an initial condition somewhere on that line, but different from the straight line solution that we already had. But clearly, multiplying this vector by a minus 2 will take this point and move it to here. And so if I create a solution and I say y of t is equal to negative 2 times y1 of t, I'm motivated to use the minus 2. I'm forced to use the minus 2 because this forces us to get the desired initial condition. This will be our solution, is a solution of the initial value problem. Erase that. That's supposed to be an I, initial value problem, because because, first of all, y at time 0 is minus 2 times y1 at time 0, which we know is 1 minus 2, and takes us to minus 2, 4. So that checks. And we also know that any constant multiple of a solution is another solution. And since we already demonstrated that y1 of t, that this solution vector solves the differential equation, minus 2 times it will also be a solution. And so we conclude that this is the solution of the initial value problem. It satisfies the initial condition, and it is a solution of the linear system. That's it.